So ethers, what are ethers?
C double bond O O.
Ethers.
Wait, that's
What
Esther.
function?
Sorry. Oh, my bad. Ma'am, I'm telling you that.
Hydrogen is
spelling
replaced
mistake.
with OR, an alkoxy group, or one more. I don't remember the second one.
It's R dash O dash R or R dash O
Yeah.
dash R dash.
R dash. So it's basically you take an alcohol and instead of OH, you attach another alkyl group to oxygen. That's it. And if you want to go like in an alkane, hydrogen replaced with alkoxy group. Okay, so those are ethers. Yeah, Ansh has sent oxygen connected to two alkyl or aryl groups. Absolutely. Okay, so ethers nomenclature we have discussed. We want like a couple of practice things just to get warmed up.
Yes, ma'am. Can you give us like questions and we'll try to solve them?
Yeah, that's what. So we have CH3, CH2, O, CH. Yeah, this is one, starting simple. And the other one would be just keep things simple just to get warmed up. Okay. Send, this is number one, this is number two. Yeah, send the names of these ethers and let's discuss this one also. The first, like the simplest aromatic ether, what would its name be? So this one, we can just give the common name. These two, I need IUPAC names. Ansh, for 1 and 2, send the IUPAC name. Okay, so Mitali and Dhriti got the first one. The second one, Mitali, you need to be more specific. You say butoxy. But stands for any.
Sorry.
And you've forgotten the nomenclature for ethers. Shantanu, you're not trying at all.
Ma'am, I'm sorry about the capital thing that Zoom just auto corrects the thing.
No, but that is not a problem at all. Like,
sorry.
Is a problem.
Yeah.
Now I'm not looking at like capitalization and all. I'm just seeing if you guys are getting the words correct. First one to theek hai. Haan, now you got it. Oh, sorry. Dhriti, Mitali, like second one, you guys did the same thing. Oh, wait, the second one, yes, Dhriti got it. That's awesome. Yes.
Ma'am, I sent a rectified answer. Like after the third one.
Nahin. No, don't see that. I think that's autocorrect.
It's not letting me type only, ma'am.
Zoom doesn't know chemical names.
Yes, got it, ma'am. Anise.
Okay, the first one, Shantanu, are you sending your answers? Haven't gotten anything from you.
I can't do it.
No? Okay. So the nomenclature, like the format follows alkoxy alkane. Okay. So there are two alkyl groups, right? One of them will turn into alkoxy, the other one will be the alkane. Now, which one is alkoxy, which one is alkane would be? This one would be the smaller alkane, will be alkoxy, and the bigger one will remain as alkane. Like for example, first one में oxygen के इधर उधर you have a methyl group and you have a ethyl group. So methyl or ethyl में methyl is the smaller group, right? So that will turn into methoxy. So you're counting this as a substituent, methyl attached to oxygen, methoxy. And the bigger one group is ethyl, so that turns into alkane, ethane. So this will be methoxyethane. Similarly, the second one, so यहाँ पे you have a methyl group, यहाँ पे you have a butyl group. So which is bigger out of these two?
Butyl.
Butyl. So that will be like, so this will turn into butane and this will be methoxy. Now, where is methoxy attached in this butane wala chain?
Miss, can you repeat what you said?
Yeah, where, like which, when I say where, like there is CH everywhere, so you need to mention the position number.
The first one.
So
Ma'am, I again gave a rectified answer.
1, 2, 3, 4, or 1, 2, 3, 4. So
1, 2, 2, the first option.
yeah, where is methoxy attached? Like 2 or 3? Which number will you consider position के लिए? Two or three?
Two.
So this will be 2-methoxybutane.
Ma'am, question. Shouldn't it be butoxy?
Why? So you're saying butoxy?
Because it's a 4 carbon chain, right? So
that is the reason, like you can take anything to be attached under oxy. Like this can be called ethoxymethane or methoxyethane. So
okay.
but like every compound will need to have one name. Like that's the whole point of standardizing it, right? So according to that, the one that gets the oxy is the smaller alkyl group, and
okay.
chain is counted as an alkane. So that is
okay, ma'am, got it. So I did that wrong because I always thought that, you know, on the right hand side they usually have a bigger thing than on the left hand side, or usually it's the same or something like that. Okay, got it.
That's the way you write it. So don't go by how the molecule is presented, because this is a 3D molecule. Like ऐसे भी हो सकता है, ऐसे भी हो सकता है. So don't go by that. Follow the rules, like count the number of carbons and all of that. Okay. And the simplest member of this thing, iska common name is anisole. Yeah. Okay. So this is nomenclature of ethers. What other points do we have? Physical properties, we'll do that after preparation. Yeah. So ethers are basically, this is the functional group ether when oxygen atom is bonded to two other R groups. Yeah. Preparation methods. So preparation of ethers is funny. So the first method of preparation is you take an alkyl halide and make.
Did you say preparations of ethers is funny?
Yeah, there's like.
Oh my god, I thought something went wrong and I'm just like, why am I hearing funny? Why did she say funny?
You'll see why. It's not funny as in like a jokey way. So this method is, so the first method is by dehydration of alcohols. So what is the reagent that you use when you dehydrate alcohols?
Concentrated H2SO4.
Right. You take an alcohol, treat it with concentrated H2SO4. What product do you get?
The H is replaced by a R group,
Right.
like a R or R dash group, substituted basically.
That is right. And you're saying that because we're talking about preparation of ethers. But if you get a question like this, ROH treated with concentrated sulfuric acid, where else have you come across the situation? In what other way can you dehydrate alcohols?
Can you come again?
Like, I'll take an example. This will make it easier. So if I have CH3, CH2, OH, and if I treat it with concentrated H2SO4,
You get ethene and water.
Beta elimination.
Beta elimination, right? So you studied that dehydration of alcohols, like by using concentrated H2SO4 causes beta elimination. So how do you prepare alkenes from that? So how do you prepare ethers from that? So that's why I said it's a little funny. So here you need to be a little careful. If you do this reaction at 443 Kelvin, like a slightly higher temperature, you will end up with alkenes. If you maintain the temperature at 413 Kelvin, then you get ethers. Yeah. So this follows elimination. But if you keep it at a slightly lower temperature, this follows your SN mechanism, SN1 or 2, depending on what alcohol you take. Now we're talking about dehydration, right? Dehydration is exclusively like SN2 mechanism. Is there an SN1 here? No, it's all SN2 mechanism. The other one has SN1. Okay, so dehydration of alcohols. So this dehydration part, like where water is removed, the water will come from the same molecule if it's at 443 Kelvin, and it's going to come from two different molecules if you maintain the temperature at 413 Kelvins. Okay. So now let's look at the mechanism itself. As always, step one, when you're doing it in acidic condition, will be protonation.
Yeah, protonation, then formation of a carbocation, and then elimination of the proton. So like deprotonation.
That is when elimination is going on. In this case,
Okay.
following SN2. So your second step.
Substitution. Yeah, so the intermediate will be formed.
Yes.
Yeah.
Yeah. So step 1, protonation. Let's take CH3OH, this alcohol. Then the concentrated H2SO4 is going to provide H+. So these electrons are going to attack the H+ or attract the H+, and you're going to get this. So this particular part where you have a positive charge on oxygen is called oxonium ion. Yeah. All right. So continue in the next page, I'm guessing. Yeah, there's barely any space here. We'll continue in the next page.
Yes, ma'am.
Okay. So everybody, like, have you guys written it down? Can I flip?
Yes, ma'am.
Okay. Shantanu, Ansh, I can't see you guys also, so you will have to respond. Either talk or type.
Just one second.
Okay. So I've come across this app for organic chemistry. It's a very basic, very simple app, but it helps figure out the reaction mechanisms and all that. I'll see, like, do all of you guys have Android phones, or does anyone use Apple?
Android.
No, Miss Android.
Android. Okay.
So far Android. Really want Apple, but like so far Android.
Okay, then I can send the Play Store link. And Shantanu, you guys also Android only?
Yes.
I have the app Apple me. I don't know if it is there. I need to check. If that is the case, I'll send you guys the link. So it shows.
And the name of the app?
I think it's called Organic Chemistry only. Yeah. Okay, I think I installed it. I'll
The app is called Organic Chemistry for Organic Chemistry. Isn't that a little boring?
I know it's a very simple, basic app, but it's the way they explain, like, oh yeah, you have a lone pair of electrons, so where the electron shift's gonna happen, it lets you know, like it gets the mechanism, it draws a clear picture of how the mechanisms take place. Yeah.
Ma'am, when is the app that you guys are working on gonna like come to us?
So we are uploading the questions, and there's like a lot of questions, right? We also want to make
Yeah.
sure the questions don't have mistakes. So a month,
Okay.
3 weeks maybe. So I'll check.
So like before board exams.
Oh yeah,
you'll be-
for sure before board exams.
So before board exam, because like I remember we did that demo thing in the class last time, and that was looking pretty good. So it's like
the working of it is pretty set in stone. Like all the things are working, getting the points and everything. So just need to upload the questions. So that's it. Cool. So step 1, we have like a protonated alcohol. So step 2 would be nucleophilic attack. So what would be the nucleophile in this case? So this was already formed, and this has a positive charge. So what would be the nucleophile?
carbon ion.
Carbon ion, kahan se? Which ion?
What could you go back a second?
What
Yes,
species do you have in the reaction?
we have.
You're taking only alcohol now.
Yeah.
So that would be the only thing that can be capable of attacking in this situation. Okay.
So R minus.
Yeah. So the same, if you're taking a singular alcohol, then yes, not R minus, R again. This
Oh, RCH. Yeah, got it.
oxygen can't stand positive charge on it, so it attracts these electrons towards itself. And because carbon is like losing electrons, it attracts the lone pair towards itself. So this oxygen will attract the slightly positively charged
CH.
yeah, this carbon atom as the oxygen is electron. So here you get so this as this oxygen takes away these electrons, gets lost as water, and the resultant species you have CH3, which is attacked by oxygen. Like sharing its lone pair. And third step will be your product is almost formed. In order to get your final product, what should be your third step?
Deprotonation.
Loss of proton.
So formation of the oxonium ion will be formed again.
Yeah, you have the oxonium ion. Now in this case, so these electrons are taken up. I drew it wrong here. These electrons will be attracted by oxygen, and it lets this proton go. Deprotonation. Basically, you have CH3OH CH3 plus. So oxygen takes these electrons, so you get your ether and H pluses like liberated back in the solution. See? Cool. So main points about dehydration is one, you need to keep an eye out on this reaction. If you want to get ethers, you need to ensure that the temperature is, the right, you have the right reaction conditions for it. So if you're not careful, you can get alkenes in the process. Mechanism follows SN2 mechanism. The nucleophile in this case is the alcohol itself. So specifically the lone pair of electrons on the oxygen in alcohol, that is what attacks the carbon atom here. Okay, so 3 steps, you get your final ether, proton back. Yeah. Now, considering that, so there are 2 main disadvantages with this process of synthesis. Okay, so considering that it follows SN2 mechanism, do you think you'll be able to prepare like secondary and tertiary ethers with this process?
No, ma'am.
No. So this process is most suitable for primary.
For primary.
Yeah. And another major disadvantage is if I take, like, let's say I want to prepare ethyl methyl ether, methoxyethane. If I take ethyl alcohol and methyl alcohol, will I get the desired product? Why not? Like mechanism.
No, sorry, could you repeat? Sorry.
Yeah, I'll just write it here. So if I take, for example, CH3OH and C2H5OH, and then I set out to do this dehydration at 413 Kelvin. My desired product is CH3OC2H5, ethyl methyl ether. So will I get my desired product by simply taking 2 different alcohols?
No, ma'am. You will actually get, you may get the product in some quantity, but other than that, you will also get C2H5O, C2H5, and CH3O, CH3. So like numerous products will be formed if this reaction is carried out, right?
Yeah. So that is another major disadvantage, that you cannot prepare mixed ethers easily. Mixed or unsymmetrical ethers easily. So because you don't know what alcohol is going to end up attacking what alcohol, like which molecule is going to get protonated, which molecule is going to act like a nucleophile. It can be any permutation combination of these molecules. So it's not necessary, like you can't predict that I'm going to get this only. It'll be a mixture of ethers. You'll get dimethyl ether and diethyl ether also along with it. So two major disadvantage in this method of preparation, which is why you have another important major method of preparation in the laboratory, which is called Williamson synthesis. Okay. So I'll talk about the synthesis itself. Oh, you guys don't have the mechanism for this thing, right?
It's just one simple reaction given, and that's it.
Reaction, okay. No mechanism for this. Okay, that's good. Okay, so some major points in this reaction. Again, it's not like very simple. So Williamson synthesis is like the preferred method of synthesis. The main thing is you take alkyl halide and sodium alkoxide. So let both of these react and you get your ether and sodium halide. This is like a simple, kind of looks like a double displacement reaction, right? So this is like the major reaction. But if you are aiming for a specific ether, you need to be careful about which Rx and which RONA you're going to take. Okay.
Can you take like an example?
Yeah. So I'll be going through like each case. So this method you can use for creating any ether: simple, mixed, symmetrical, asymmetrical, primary, secondary, tertiary. Like any ether can be prepared using this method. So the mechanism followed here is also you have an SN2 attack of the alkoxide on the Rx molecule. So this is the major mechanism that's followed. Dhriti, all good?
I was just writing and sorry. Everything's fine.
So you have negatively charged ion, right? Now, because like the reason you're taking sodium alkoxide is because sodium is highly electropositive, it's ionic. So RO minus, this particular species' ion, is an extremely strong base and it's a very strong nucleophile, you can say. So this is the nucleophile that attacks Rx. So how do you decide what molecules to, like what species to take for any particular ether? So because you have like to get the ether, the RO minus, the alkoxide ion, needs to do a SN2 attack on Rx. Now because it's an SN2 attack, primary alkyl halide is your best bet to prepare these ethers. Secondary also you can manage, but it's not ideal. You cannot take tertiary alkyl halides at all because this is going to end up with elimination reaction, not SN2. Okay. So because of this constraint, if you want to prepare like secondary or tertiary ethers, you need to ensure that that secondary carbon or the tertiary carbon is in the alkoxide ion. You cannot take secondary or tertiary alkyl halide for that reason. Okay. So the reason for this is because RO minus is a really strong base, and if you take a tertiary alkyl halide, you're going to get a carbocation formed, and like the elimination will take precedence over substitution under those conditions. Okay. So main points: Williamson synthesis, you can prepare any kind of ether. For simple ether, it's pretty straightforward. You take the same alkyl halide and alkoxide, sodium alkoxide. But if you're preparing mixed ether, your Rx should always be primary. If you want to prepare like a secondary or tertiary this thing, you're better off having that secondary or tertiary carbon in the alkyl oxide base instead of the Rx molecule. Okay, so this is like the main point about it. So the reason why this would, like in the case of tertiary alkyl halide, it would go with elimination reaction is because of steric hindrance. Steric hindrance is one problem, and another problem is because RO minus being a strong base attacks the carbocation. That it's a little complicated. So it'll take the role of a base rather than a nucleophile in that situation. That's what happens. Okay.
Ma'am, just a second.
Yeah. Let me know when you've like noted it down, then we'll go forward.
Done, ma'am.
Done, ma'am.
Shantanu, Ansh, what about you guys? Ready?
Ma'am, can you just excuse me for a minute? I'll just go to the washroom and quickly come back.
Shantanu, Ansh. Ansh is done. Shantanu, did you say something? I didn't get that.
No, I didn't say anything.
Okay, have you got all of this down?
Yes, ma'am.
There are a couple more other preparation methods. These are not there in your textbook, but just in case, just keep it noted down in case you get any questions. So one is you can also prepare this. Yeah, you can also prepare ethers by like making alkyl halides react with dry silver oxide. Okay, so this is how the reaction is. You have two alkyl halides. Dry silver oxide is basically Ag2O. This is the silver oxide that you use. So you have Ag attached to O. So the silver molecules like they basically exchange the anions that they're bonded to. Okay, so this will give you ROR and 2 molecules of silver halides. Essentially, this bond breaks. So these two get bonded. This bond breaks. Like silver basically takes the halide atoms or turns them into ions, and these two get attached to oxygen. Basically. And the fourth method, okay, this is not exactly a method of preparation as such. This is more of, if you already have like a small ether and you want to extend
The Grignard reagent.
Yeah.
Thing, right?
Yes. This is extend or prepare higher ethers. Grignard reagent is always like the same format of equation. Okay. So you take an ether, something like CH2 attached to a halide ion, and use Grignard reagent. Then Grignard reagent always takes away your anion from, or the next, like anything that has a tendency to form anion, like halide ions, OH minus, things like that, and attaches the alkyl group to it. So you get, let's call this R dash. You get ROCH2 R dash and MgX2. That's it. So yeah, these are like the 4 methods of preparation. And then we'll talk about their physical properties. So again, let me know when you guys have done this, and we'll go on to the physical properties. So 2 more extra methods of preparation. So you've got alkyl halides with dry silver oxide. They basically exchange their, I don't want to call it negative ions, but yeah, like the non-metals basically. Yeah. And again, using Grignard reagent, like it's not exactly a method of preparation. It's more of, if you want to attach an alkyl group to already an existing ether, by like you want to prepare a different ether from an existing ether, use Grignard's reagent.
Yes, ma'am, done.
Done, ma'am.
Shantanu, Ansh? Done. Okay.
Yes, ma'am.
So let's talk about physical properties. We'll go to the next thing. Physical properties, we have already discussed a little bit of it in comparison with alcohols when we were doing alcohols. So let's talk about solubility and like boiling points, okay? So what can you say about the solubility of ethers? So ether ROR dash, do you think they will dissolve?
Not as readily soluble as alcohols and phenols, but they'll still be like sparingly soluble in water because O is present. So like some sort of hydrogen bonding will be formed with water. So they will be soluble.
So tiny correction, if you compare them to alcohols, they are as soluble as alcohols. So the deal with alcohol,
Okay.
the smaller ones were like properly soluble till like C3 or C4, and the higher ones, as the number of carbon atoms increased, they become increasingly like sparingly soluble in water, right? Increasingly insoluble. So it's the same with ethers also. The smaller ethers are soluble in water for the exact same reason. The oxygen is capable of forming hydrogen bonds with water. the bigger ones, then it starts, the solubility starts decreasing as the number of carbon atoms increases. So the comparison is, here you have to compare, like for example, if you compare C2H5O, C2H5, iska solubility will be almost same as butanol. So that's another factor you need to keep in mind when you're comparing it. Yeah, so their solubility is comparable to those of alcohols, but as long as those alcohols have the exact same weight. Okay. Next, talking about the boiling point, boiling or melting point.
Miss, the boiling points, I think, of ethers is much, boiling and melting point is much lower than that of alcohols as compared to alcohols.
That is correct, yes. So even though the solubility is comparable, when you look at the boiling melting point, it is much lower than.
I guess it is mainly due to the H bonding.
Yes, absolutely. So H bonding is possible in water for solubility because water has those hydrogens that the oxygen can bond to. But if you just have simply ethers, there's only oxygen, but there's no positive charge for it to bond with, right? So because of the absence of H bonding, it is much lower than alcohols. You can say it is fairly comparable to alkanes. Again, when we are comparing alcohols, alkanes, like similar molecular mass. So the order of boiling melting points is kind of like this. So alcohols are like much, much greater compared to ethers. And ethers ka is like slightly greater than alkanes. No? Like if alkane ka, any specific alkane ka boiling point or melting point was at, let's say, like 40 degrees Celsius, ethers would be more like 43, 44 SA, like slightly higher, but kind of in the same range. And alcohols would be like 70 something, like much greater, lot of difference. So these are like the physical properties of ethers. Okay, what else do we have? Again, if you're looking within ethers itself, it increases as the molecular mass increases, as always. The reason for both, like why this is all completely because of hydrogen bonding. The context is different. Like solubility happens because ether has oxygen, water has hydrogen, like with the slightly positive charge, and that's why the hydrogen bonding is possible. But that is absent when you take a pure ether. That is the reason the boiling melting point is also reflective of it. It's not high like in alcohols. Okay. Then chemical properties. Chemical properties of ethers also you have like.
Miss, 1 second, can you show the previous page? Sure, but we can just use
Chemical properties, you just have one reaction mechanism and then electrophilic substitution. Oh, that's it. Cool. Let me know when you guys are ready to start with the chemical properties.
done. You can start the chemical properties.
I'm Shant, I'm waiting for you guys.
Yes, ma'am. You can start it.
Okay. Ansh, okay. 1 minute. Okay. Note down.
So, ma'am, tomorrow we're going to have an offline lecture from 9:30 to 1:30, right? As usual.
I'll send the message. I'll inform you guys.
Oh, okay, ma'am.
Okay.
So, basically, we don't have math tomorrow, right?
Probably not. Yeah, I'll just check. I've checked with Rishabh sir if He needs a lecture in case you guys need more practice in that, but mostly not.
Okay.
All right. Chemical properties. There's only like one reaction. So ether, if you look at it, it is ROR. So the only like whatever reaction you do, it's basically cutting the CO bond. Okay, that's the only kind of reaction that you do. Which again, ethers are one of the most inert substances in all of organic chemistry, or you can say one of the least reactive substances. That is the reason, you know, they're used as solvents in a lot of reaction. Like you come across a lot of reaction conducted in dry ethers because ethers are basically just chilling out, like not interfering with anything, not reactive at all. So, okay, let's not call it least reactive, like one of the least reactive, not the least reactive. So they are slightly more reactive, like if you had to look at other things, so they're like slightly better than alkanes, cycloalkanes. Yeah, basically they're just like slightly better than these compounds. So let's talk about the reaction. So the only reaction that they will undergo is to break the CO bond. So this bond can be broken only under drastic conditions. So drastic conditions in the sense you need to take really high quantities of acids, you need to control the temperature, like high temperature, that sort of thing. So with excess HX. So even this HX, usually you use HI and HBr because they are the only ones that are sufficiently acidic enough to break that bond. Yeah. So the main reaction is you have ROR. Like, so there's two versions of this reaction. Okay, one is if you take a simple ether, it's pretty straightforward, the kind of products. But if there's a mixed ether, then you need to look at what the two alkyl groups are to be able to figure out the product. So I'll take both the cases separately. It'll be easier to follow. So in the case of simple ether, you take this, treat it with HX. Pretty straightforward. One of these bond breaks. So you end up getting an alcohol and an alkyl halide.
Either one bond is broken, the product will still remain the same because it's a simple ether, right?
Yeah, because both the R groups are ethers. So, I mean, the same alkyl group. So it doesn't make a difference whether this breaks or this breaks.
Yes, ma'am, got it.
And if you're taking like excess HX and you're slightly increasing the temperature, then whatever alcohol is formed, right? Even that will react with HX and produce, yeah, more RX. So this is when you have like excess HX and at a higher temperature. Okay. Another standard is, again, if you're doing any reaction with anisole or aromatic ether, then here also, like, even though it's asymmetrical, you don't have to wonder, like, this is also pretty straightforward. Blindly, you can say, so which one will be alcohol, which one will be alkyl halide? So which bond is easier to?
Phenol and ROH.
Phenol and ROH.
Oh, RX, sorry.
Hmm.
Haloalkane.
Yes.
Yeah.
Yeah. The reason for this?
Due to the partial double bond characteristics of the O bond, it's going to be very difficult for it to break. like just completely break away. So
Yes. So basically, this particular bond, like CO bond between the
the phenoxide ion. So ma'am, do we show, not like it's a subjective paper, but like the phenoxide ion ka resonance?
up to you. So
Okay.
like that is definitely a factor. So phenoxide ion resonance, it has partial double bond characteristic. So this is
Yes, ma'am.
much stronger. So it will be harder to break. So always this bond is going to break. Okay.
Yes, ma'am. Got it.
Straightforward. This is in the case of simple ethers. Now, when you have asymmetrical ethers, okay. So before we get into this, like for this, we'll be getting into the mechanism of it. So before we do that, you guys noted this down?
Just a minute, ma'am.
Just 1 second.
You can stop the reaction here, but you need to like be really controlled. So if it's not controlled, then this alcohol also is going to get converted because you have a lot of this HX.
Done.
Done, ma'am.
Shantanu?
Yes, ma'am.
So in the case of asymmetrical ethers or in unsymmetrical ethers, complex ethers. So again, the format of the reaction is the same. You have ROR dash with HX. It's gonna break. So hydrogen is gonna go one side, halide is gonna go on the other side. So again, you still get RX and R dash OH. In this case, always you have Rx is formed with the less bulky group and ROH is formed with the more bulky group. Okay, so if you have lesser number of carbon atoms on one side, that is going to, let's keep it R dash, yeah. So whatever forms alkyl halide, like the less bulky, like if you have lesser number of carbon atoms, that is going to form your alkyl halide. More number of carbon atoms, bigger groups, like secondary ones, they are going to form alcohols. Okay.
Yes, ma'am. Got it.
We'll get into the mechanism. So mechanism, I'll divide the page into two. Okay. So step one. Okay, can you take a random guess what step one could be?
Protonation.
That's it. So you have HX. The only thing is H plus will attack the lone pair of electrons on this. Okay. So I'll take a unsymmetrical alcohol, or I'll keep, like for step one, I'll keep it generalized because it's the same thing either way. ROR dash. You have lone pair of electrons here. You have H plus I minus, let's say. So these electrons are going to attract the H plus from here. So your step one is always protonation. Okay. Now your step two is going to be either an SN2 attack or an SN1 attack. So can you predict when do you get SN2 and when do you get SN1?
We'll get SN2 with the less bulky and SN1 with the more bulky.
The
Because
more bulky.
yeah, more bulky means it has more methyl groups attached to it.
So tertiary usually prefers SN1, primary usually prefers SN2, just like with your other substitution reactions also. Okay, so now I'll take like specific examples because we're using like different things. So if you have a primary carbon, so let's say you have CH3, O, CH2, CH3. Okay, everything is primary in this case. We have plus H. So this is what we got at the end of step 1. The I minus that is there, let's write it on this side. The halide ion will be your nucleophile. So this is going to attack, again, same as what happened in the dehydration process, the same thing. So this oxygen has a positive charge, so it's going to attract electrons. So I minus going to attack the primary this thing. What you get is CH2, CH3OH, and CH3L. Okay. So of course, like you have the intermediate formed. So when this attacks, so you have I, then CH3, then OH, CH2, CH3. So this is your intermediate. Okay. So nucleophile attacks the primary, like the less bulky one, where there is no steric hindrance, so that this intermediate can be formed. So as this bond is forming, this bond is breaking, and when this completely breaks, you have these two products. Now, in the case of SN1 mechanism, like let's say instead of CH2, CH3, I have a tertiary this thing. Again, tertiary carbocations are always extremely stable. So when you have that sort of a species, again, CH3O plus protonation hua, then I have C, CH3, CH3, and CH3. In this case, tertiary carbocation is really stable. So this carbon doesn't mind giving away its electrons. So this is going to break, like it's going to give the electrons here. So I'm going to get CH3OH and the tertiary carbocation. Okay. Then once I have the carbocation, the I minus that is formed over here, right? So that's going to
will attach to it. Yeah. So like a electrophilic attack.
It's still nucleophilic. I minus is still a nucleophile. No, wait.
Sorry, nucleophile. Yes, nucleophile. My bad.
Nucleophile in both cases. Okay, so it's the same nucleophilic substitution.
Please don't go below this, I won't be able to see.
We're done with the mechanism, that's it. Okay, so it's the same thing in both the cases, just the mechanism is where it's going to differ. And so in that regard, then the statement is wrong. Like we can't say always. Like if it is tertiary, you're going to get an alkyl halide here. Let's say mostly.
But ma'am, I didn't get it.
So earlier I said Rx will, like the one that forms halide is always less bulky and alcohol is formed by more bulky group, right? But if you have a tertiary ether, you're getting the halide with the more bulky group because of the formation of carbocation. So this is wrong. So instead of saying bulky, you can say less number of carbon atoms, more number of carbon atoms, as like, you know, if you have both primary or both secondary, that sort of a thing.
Yes, ma'am. Got it.
So
Done, ma'am.
yeah, so if you have like primary, secondary, tertiary, like basically you need to just look for the presence of tertiary carbocation. So if you have tertiary, the halide ion will be attached to the tertiary this thing. Okay. Shantanu, Ansh, you guys have noted?
Done, ma'am. Done. I am done writing. Done. Right?
Yes. Okay, Ansh has noted. But you guys, like, is this clear? When do you get what product, which alcohol you get versus which halide you get?
Yes, yes, ma'am. Yes, it's clear.
So note this down clearly, because when you do the questions, if you come back to refer to it, it should not be confusing. Like you should be able to have a clear cut thing. Okay. And the mechanism, like if you have excess HI, as always, if, or instead of saying if, in excess HI and at higher temperature. So you guys know the mechanism of conversion of alcohol to the alkyl halide? What's up, Kriti?
Ma'am,
Just
could you
seeing
repeat
my
that?
sister doing
Just
dot dot dot. Let's leave it at that. Miss, don't worry, I'm paying attention, 100% attention to what you're doing. I know what you're doing. I'm writing everything down, so you don't have anything to worry.
Like, yeah, I just want to ensure you're not distracted. Reach me if you miss something.
Ma'am, could you repeat that?
Yeah, so in the case of when you have excess H, or HX, basically hydrogen halide, and if at a slightly higher temperature, then the mechanism of how the alcohol that is formed is converted to HI, or the alkyl halide. And it's the same thing, nucleophilic substitution.
Yeah.
The,
So the OH, yeah, will be attacked by the H plus, and the H plus will like, so it will become a positive thing. Then there'll be like a hydride shift.
yes. So this,
Is I right about the hydride shift?
what do you mean by hydride shift?
The positive charge will shift and form a more stable. No, wait, it's in tertiary. Sorry. Yeah, because I remember, ma'am, like there was this question in the QB, and then something was supposed to form, but in the end, it became like a tertiary thing. Why tertiary? Because it's more stable. So the hydride, the positive thing, charge shifted. Yeah, to gain more stability, and then the product was something different altogether, like the naming thing.
That happens, yeah. So whenever you have like, you have a primary thing, and then side may, if you have a tertiary thing, then the positive charge will shift to enable the
Yeah.
Yeah, and yeah, that's it for this thing. So anisole ke case mein again same thing. And then this is specific for anisole. It undergoes electrophilic substitution. Do you guys need to go over electrophilic substitution again?
No, ma'am. We've done it like too many times now.
So you guys only predict the product. So we have anisole reacting with, let's go with Friedel-Crafts reaction. Okay. CH3Cl, Friedel-Crafts alkylation in the presence of AlCl3. So what are the products? Also, like in case you get like a major product and minor product, also specify it.
Ma'am, we put the chat box or like.
Ma'am, can I say it because it's too long to write?
Yeah, you will have to type the entire name. Yeah.
Okay, Mitali can give the major product, I'll give the minor product or vice versa.
Yeah. So the major product is anisole, and the CH3 will be in the para position. That's the product.
Para
Yeah.
anisole.
Not
Yes.
para.
Not para and sorry. So it'll be like
Okay.
methoxyanisole.
Major product. So draw anisole then.
And minor product it'll be paramethoxy anisole, right?
Oxyanisole or something else anisole.
No, methoxy.
Look at the reagent, Friedel-Crafts में. What are you attaching here? Look at this.
Methoxytoluene.
Toluene.
Yeah.
So paramethyl.
And minor will be orthomethoxytoluene.
Yes.
So, whatever.
Yes, ma'am.
Yes. Absolutely.
Ma'am, with this, the chapter is over, right?
Yes.
Yay. Finally. This thing is so long, it wasn't getting over only.
Yeah, we spent almost like 4 classes on this. So now we are left with solid state and
P block. Ma'am, P block mean there is like so much reduction in P block.
Group 7.
Like oxides are not coming. Group 17 as a whole is coming, but it's oxides of halogens are, I think, they're not coming.
Okay.
But like basic information you need to know about them. Example, trends.
Group
Like
wise.
that's what we're discussing. Yeah. Then group 18, I don't think there is any reduction. But like especially for the group 15 and 16 thing.
Oh yeah.
They've removed oxides, all the oxides. They've removed structures. They removed all the compounds as well, phosphine and now I don't remember, but like yeah, stuff like that.
So you just have like the overall group trends for group 15, 16, 17, 18.
Yeah.
So I'll focus more on solid state then, and then if we have.
Yes, ma'am. Even in solid state, nothing after electrical properties is coming. So like until the defects, point defects, metal defects.
You still have a major thing, no? Like
yeah, that's still a big thing. Yeah, but like just like some part of it, like piche se, like 2-3 pages are not there. Yeah. So do we start with solid state like right now or like tomorrow?
Up to you. No, like tomorrow Ansh is not there. No, there'll be no point starting a whole new thing. We could start with solid state. Yeah, lots of time.
But solid state is not that difficult of a chapter.
Yeah, it's very easy. I mean, things we know just in a more depth way.
Yeah.
I guess.
There's a lot of memorization, like you need to know the Bravais lattice, the cubic cells,
Yeah.
that
The 14 types of Bravais lattice. No, seven types. 14 types, 7 types.
14 units.
14 units. Yeah.
The main thing
Horrible.
I'd like to focus on is figuring out the formula of a compound.
The tetrahedral voids and octahedral voids, wala thing. Okay.
And also, like, you have numericals, like if 1 mole. So they give you information about the structure, and then you have to figure out what is the formula of the compound.
So, ma'am, can you somehow record a physical lecture?